Well, hello everyone. So we are going to resolve issues with multi-head attention, and since we're building the Autograd and computational graph, it seems like our multi-head attention backward pass, the computational graph is actually breaking, and for some odd reason, I could not record the previous video. I had to delete that one because it was actually a 42 minutes long video in which my camera was working just fine, but my screencast it was stuck on one single frame. So I thought that um, I have to make a debugging session on it again, and let's see how it goes. So yeah, fingers crossed this time, and let's see how it goes. So this is going to be the video. We have to code some maybe we have to code a little bit, and most of the time we'll be debugging that what exactly is wrong, since we are actually there's something wrong with our scale dot product attention function, because it seems like it's not working fine, because we're getting the initial logic fine, because we're able to make the projections, output correct, and and by projections I mean for scale dot product attention we need queries, keys, and value matrices, which we're getting just fine, and I'll show you just now, printing them all. The slicing columns logic is fine, because we need to slice the heads out of the one big tensor, and slice the heads of rows versus dk dimension, which is the head dimension, and we're getting everything fine. Keys, queries, values, and um, keys matrix, everything is working fine, but it seems like there's something wrong with the scale dot product attention function. We have corrected our softmax function, which is working just fine. We have individually test every single method, and let's see what exactly goes wrong. So fingers crossed to me. Bismillahirrahmanirrahim. Let's get started with this. So in case if I show you, where's my I cannot decrease the font size because you guys will not be able to see, but if I increase the font size, um, the issue is this. If I open the run file, you see I'm getting multi-lines for a single line, right? So that's the issue. But the thing is, I'm recording this on my laptop, which is 144 hertz, and you see much smoother typing experience. If I record on my 32 inches Lenovo 60 hertz, it feels a little jerky, and nobody has actually complained this, but I myself feel that it's not as smooth as one can like. So yeah, so let's just record on my laptop, and that's the only option available right now. So okay, and I cannot decrease the font size either. So this is my run file, and I have commented these two lines, and this is something that I'm going to run. So if I run this, let me just open this my editor, and this is going to be my terminal. I'm using tmux over here, and one thing that I can do is I can just remove these domain and username, so I'll have some space available over here which I can utilize, and I'll look into it later. So so let's run this file. So you see what we're getting over here. So yeah, this is what we're getting over here. So I'm just printing. This is actually a sliced version of my query matrix, and sliced version I mean that initially I had 16 cross 32 matrix, and then I sliced them, dimension, embedding dimension divided by number of heads, and I got this particular column for each particular head, right? So in multi-head attention, what we do is we create multiple heads, and the purpose of these multiple heads is just grasp as much contextual or semantic knowledge as you can of a particular language. So one head would be responsible for grammar, the other would be like sentence arrangement, patterns. So it helps overall pattern recognition, features extraction of a language if you use multiple heads instead of one single head, right? So once we develop this successfully, once we can run this forward and backward pass, later on we'll go into this thing. Okay, this thing as well, we will not split the heads, and we will do it for one single head, and let's see what difference does it make. So hopefully inshallah soon we'll be on that stage. And right now, if I show you here, okay, so this is actually attention 5. So if I go inside the forward method, forward, this is multiple head attention forward, and you see what we're doing is actually we're getting these big matrices, q, k, and v, by using tensor manual operation. So far it's very good. And then we are also printing these, and we're looping through gate number of heads times, and for each head we are actually splitting the columns, passing this k and dk dimension, right? So along the columns dimension it will split, so it will keep track of Yeah, this is actually an important point to notice. Yeah, so next time the k will be 1, and it'll jump k times, so dk, it will jump the stride of k times dk, and initially k is 0, so it'll be like starting from 0. So if I, in case if I sketch this out over here, it's a very important thing. You need to understand this if you are someone who like algorithms, and who just want to create their own transformer and maybe play around with the matrices. This is important concept, so that's why I need to pull up this sketchpad over here. So what I mean by this, so initially what we have is we are looping k from 0 to number of heads times, right? Number of heads times, right? And so initially the k is 0, and we take the stride dk multiplied by k, right? So for k is equals to 0, this is going to be 0, and this is all going to be 0, so starting index will be 0. For k equals 1, so our stride would be, this dk is like, let's say it's 4, maybe 4, and how do I know it's 4? Because 32 divided by 8, that makes it like 4. Yeah, so this is our embedding dimension, and this is our number of heads. So that's how you calculate this dk, each particular head dimension. And what happens basically is, yeah, so 4, and this is 4 multiplied by 1, so the starting index would be 1. And for k equals 2, this 4 is going to be multiplied by 2, so this time it's like 8, right? So this is 4, okay, 4, 8, 12, and that's how it will go. So what we're doing actually is we're jumping. So this was actually, since you can say this was actually our main, you can say 16 cross 32 matrix, 32, right? And we started from here, we went till here, this is actually the third, and then we started from here, this is 4, and we went till 7, right? And then dk is like from 8 to 8 to where, like let's say 11, and then 12 on, so till 32 we go like this. So what we are doing actually, we're making slices of these columns, and this inside this particular like plane, I used to call, I actually prefer to call it a plane, because it gives me a concept of Cartesian coordinate system, in which you can understand as well. The x and y dimension both are called as plane. The x, y, and z dimension is called as cube, right? So funnel seed time. All right, so we split the columns, right? And we tested this, right? So this is our head 1, this is our head 2, this is our head 3, and that's what we are doing over here, right? So if I one more time run this, so you can see this was actually q, right, at k equals 0, and this is actually k at k equals 0. This is actually v at k equals 0. So we go for from 0 to 7 for all. So we need to, you see, we are adding a depth, right? This is something we call depth, right? So something like this. Let me just show you. So something like this. For example, if I try to draw it over here, so what we are doing actually, this is our cube, right? And this is our k, and this is our, oh dear, okay, why don't we just okay, so this is our q, this is our k, and this is our v, right? So these two are, this k transpose is get multiplied, tensor multiplication denoting this add sign, this is q, and then we sort of build a graph for this scale dot product regression. Later on everything happens, and this v comes into play. We multiply it to get the attention score final. So this is actually, let's say let's just call it k q at k equals 0, right? K 0. This is k at k equals 0, right? This is v at k equals 0, correct? And then what happens is, when we split the heads, they're stacked like this, on top of each other, right? So this is going to be, I'm really sorry for the diagram, for k equals 1, and this is again, we're just stacking, right? Stacking this dimension on top of each other to give you an idea that it works as depth, as 3D, right? So this is k at k equals 1, right? And this is also v at k equals 1. So go on and on to find k, q, k equals 7, the last number of heads starting from 0th index to this one, and this is going to be like this, right? So what we do is we sort of each time for this k equals 0, k equals 1, from k till number of heads for all these projections, and I used to and I prefer to call the projections because this is actually a right terminology to use, right? So each time what we do is we use at particular k index to calculate this using this formula, right? Using this formula, let me tell you the formula: q times k transpose under the root of dk, which is actually the dimension for our head, and this is actually the softmax. We apply softmax on it like so, and then we multiplication like v, and this is our score, right? So this is actually the formula that comes from the paper. Attention is all you need. Enough of the explanation. Let's go down and try to address the issues. What's wrong? So one last thing, we're getting at particular k index every q kv, since our projections are completed just fine, calculated just fine. We have tested it where we have tested it over here, okay, in this tensor file, right? So we tested every single thing. We created chunks, we sliced them, we concatenated them. We have actually element wise compared that whether this particular position of the element is correct in slicing and concatenation both. Everything was working just fine. Now what could be wrong? Definitely there's something wrong with the scale dot product attention, because we're getting all the projections correctly, but we're not able to get this computation score, right? Computation score, that is which I just shown you the formula, uh, q times k transpose or whatever, right? So let's get into it, and without further talking, let's go and see how it goes. Scaled dot product attention. Tensor fill value. Let's just see if this works. So I think I need to exit this tmux for now, and okay, so vim 2, and let's just create some other matrices, and this should be z, and randomize y and z, right? So like so, x, y, and z, perfect, makes sense. And let's just comment this thing out to see what exactly is wrong with this method called scale dot product attention. We need to figure out what exactly is wrong, because we're not getting their head attention score, so there must be something wrong. But surprisingly, we actually tested this method, which was working just fine. So let's just do it one more time. So let's say if I have tensor out and takes what, arena x, y, and z, and tk, and tk is, let's say, 4. Let's just statically or manually type this, and tensor shape including what out, and so we're getting something. It means that everything is working fine, but there's something wrong with our projection tensors, and projection I means q, k, and t. So let me do one more thing. So If I come over here, and if I go inside scale dot product tension, where is it defined? It's defined over here and over here, and printf tkk tensor. uh, let's see if this thing works fine. DKK tensor, we're getting this fine. We're getting this fine. Mm, what shape does it has? Okay, I think, see, the strange thing is, see over here. So, um, we have created tensors, right? We have created some test tensors in order to check whether this scaled dot product attention method is working or not, because that's the only thing on this particular function we are facing issues with our uh, multi-head attention forward pass. So we just wanted to check whether it's working or not. So I just created random tensors of the shape sequence length by embedding dimension. So this is working fine, but our actual embedding dimension in multi-head attention is dk, which is like 4 in our particular case. So let's just do one thing. We are explicitly setting this as 4 to match the dimension, to match everything, and see if this will work or not. Right? So we have 3 tensors of this shape, right? And our dk is also 4, and let's see if we get something. Okay, so um, tensor out. Looks like we are getting. So okay, so let's just do one more thing. Uh, to further confirm that if everything is working fine over here, attn2. So let's just do one thing. And printf head output. So this is going to be our head output. Boom, 16 cross 4. We're getting this, right? We are getting this. Now let's go back to our attention file. Forward. Scale dot product attention. This takes 3 tensors and dk and arena, and it just takes the transpose, and voila, it just works fine. Tensor division, tensor map. Well, it just works fine. Okay, and forward. This is MHA forward, and head score is scaled dot product attention QK KK VK. Okay, so QK is this slice columns, and KK okay, so This is working fine. Tensor get 2D KK. This also works fine. And what VK? So QK KK VK. So QK KK VK. What exactly is wrong here? Okay, so this is our MHA create new number of heads, sequence length, and embedding dimension. And what is our X is going to be embedding dimension, initialize parameters, multi-head attention for pass, all zeros, 1632. 0, 0, 0, all zeros. Okay, that's a good sign. That's a good sign actually, because all zero means if either the tensors are not initialized, and we can check everything. Okay, so this is actually our X and this multi-head attention. So we did not initialize this X. So let's say turn the randomize X, and let's see what we get now. None. Dude, something is wrong with the calculations, right? Head score. Something is wrong with the head score. Can we use like tensor randomize weights over here? Um, tensor MHA create. Let's just do one thing. So let's just do tensor randomize weights. Ah, voila! We were initializing this incorrectly. Right? Okay, so this seems like it worked. Right? So we need to further test it. It seems like it worked, but there's also one thing at the bottom, that is this thing. Our best friend, our bestest friend, Segfault, our bestest friend, which means either we did not initialize the memory and we are trying to populate something on that memory. First thing. Secondly, we are going outside the bounds of initialized memory. So there's only two reasons we face this. Not only two reasons, but those are the only two reasons that I know. Could be something else as well. So we're getting closer. One thing that I want to test is okay, let's just go inside the for method, and now what we can do is we can just put a break there, and let's see individually if heads are working fine. Okay, the individual head is just working fine. Why are you getting this error? Okay. Um, head score. This head score is working fine. And we should not return null now, or we should not. What we should return, like, oh. We need to return this thing and just remove this break. Yeah, tensor concatenate, and let's see if we get something now. So we're printing over here shape 2D. Shape should come down because like so. Voila! We were returning a null pointer. We should return MHA out, which is actually the right tensor to return. And wow, we are getting 16 cross 32. Seems like our MHA forward pass is just working fine, right? And now we need to integrate these things inside our main, and let's see how it goes. So there it is, our main MHA forward. So we are fine till here. Big congratulations. We're doing good. We're building computational graph. Everything is working just fine. And we've successfully run our MHA forward as well. Right, now we need to clip the gradients to, keep them inside a bound. They should not go outside for gradient explosion or gradient vanishing. Explosion, actually. We're getting the shape of the tensors. We're getting the shape of this. We're checking the tensor. Is everything is good? Apply layer norm, which is working just fine. And let's do one more thing over here. So tensor get 2D A to TN score. Let's see if our actual and we are gonna exit then run multiple definition. That's correct. uh, Ooh, lots of non-values, but this has to do with something else. But our initial head multi-head attention is working just fine. This has to do with the initialization of weights. We will be fixing that in the next episode, and I'll see you in the next one.